not integer arithmetic, n, on full 1 to 8 bits quantities in parallel. Intel's Sunday Bridge processors added the advanced vector extensions, AVX, instructions, widening the SIMD registers to 256 bits. The Intel initial many-core instructions implemented by the Knights Corner Xeon Phi processors, and the AVX 512 instructions implemented by the Knights Landing Xeon Phi processors and by Skylake X processors, use 512-bit wide SIMD registers. Current implementations. During execution, current X86 processors employ a few extra decoding steps to split most instructions into smaller pieces called microoperations. These are then handed to a control unit that buffers and schedules them in compliance with X86 semantics so that they can be executed, partly in parallel, by one of several, more or less specialized, execution units. These modern X86 designs are thus pipelined, superscalar, and also capable of out-of-order and speculative execution, via branch prediction, register renaming, and memory dependence prediction, which means they may execute multiple, partial or complete, X86 instructions simultaneously, and not necessarily in the same order as given in the instruction stream. 19. Some Intel CPUs, Xeon Foster MP, some Pentium 4, and some Nehalem and later Intel Core processors, and AMD CPUs, starting from Zen, are also capable of simultaneous multithreading with 2 threads per core. Xeon Phi has 4 threads per core. Some Intel CPUs support transactional memory, TSX. When introduced, in the mid-1990s, this method was sometimes referred to as a RISC core or as RISC translation, partly for marketing reasons, but also because these microoperations share some properties with certain types of RISC instructions. However, traditional microcode, used since the 1950s, also inherently shares many of the same properties. The new method differs mainly in that the translation to microoperations now occurs asynchronously. Not having to synchronize the execution units with pedecode steps opens up possibilities for more analysis of the buffered code stream, and therefore permits detection of operations that can be performed in parallel, simultaneously feeding more than one execution unit. The latest processors also do the opposite when appropriate. They combine certain X86 sequences, such as a compare followed by a conditional jump, into a more complex micro-op which fits the execution model better and thus can be executed faster or with fewer machine resources involved. Another way to try to improve performance is to cache the decoded micro-operations, so the processor can directly access the decoded micro-operations from a special cache, instead of decoding them again. Intel followed this approach with the execution trace cache feature in their NetBurst microarchitecture, for Pentium 4 processors, and later in the decoded stream buffer, for core-branded processors since Sunday Bridge. 20. Transmeta used a completely different method in their Crusoe X86 compatible CPUs. They used just-in-time translation to convert X86 instructions to the CPU's natively instruction set. Transmeta argued that the approach allows for more power-efficient designs since the CPU can forego the complicated decoder step of more traditional X86 implementations. Segmentation. Mini-computers during the late 1970s were running up against the 16-bit 64 KB address limit, as memory had become cheaper. Some mini-computers like the PDP-11 used complex bank switching schemes, or, in the case of Digital's VAX, redesigned much more expensive processors which could directly handle 32-bit addressing and data. The original 8086 developed from the simple 8080 microprocessor and primarily aiming at very small and inexpensive computers and other specialized devices, instead adopted simple segment registers which increased the memory address width by only 4 bits. By multiplying a 64K address by 16, the 20-bit address could address a total of 1 megabyte, 1,048,576 bytes, which was quite a large amount for a small computer at the time. The concept of segment registers was not new to many mainframes which used segment registers to swap quickly to different tasks. In practice, on the X86 it is a much criticized implementation which greatly complicated many common programming tasks and compilers. However, the architecture soon allowed linear 32-bit addressing, starting with the 80386 in late 1985, but major actors, such as Microsoft, took several years to convert their 16-bit based systems. The 80386 and 80486 was therefore largely used as a fast, but still 16-bit based, 8086 for many years. Data and code could be managed within near 16-bit segments within 64 kilobytes portions of the total 1 MB address space, or a compiler could operate in AFAR mode using 32-bit segment offset pairs rehatching, only 1 megabyte. While that would also prove to be quite limiting by the mid-1980s, it was working for the emerging PC market, and made it very simple to translate software from the older 8008, 8080, 8085 and Z80 to the newer processor. During 1985, the 16-bit segment addressing model was effectively factored out by the introduction of 32-bit offset registers in the 386 design. In real mode, segmentation is achieved by shifting the segment address left by 4 bits and adding an offset in order to receive a final 20-bit address. For example, if DS is a 000H and psi is 5677H, DS psi will point at the absolute address DS10H plus psi equals a 5677H. Thus the total address space in real mode is 220 bytes, or 1 megabyte, quite an impressive figure for 1978. All memory addresses consist of both a segment and offset. Every type of access, code, data, or stack, has a default segment register associated with it. For data the register is usually DS, for code it is CS, and for stack it is SS. For data accesses, the segment register can be implicitly specified, using a segment override prefix, to use any of the 4 segment registers. In this scheme, 2 different segment /offset pairs can point at a single absolute location. Thus, if DSISA111H and psi is 4567H, DS psi will point at the same of 5677H as above. This scheme makes it impossible to use more than 4 segments at once. CS and SS are vital for the correct functioning of the program, so that only DS and S can be used to point to data segments outside the program, or, more precisely, outside the currently executing segment of the program, or the stack. In protected mode, introduced in the 80286, a segment register no longer contains the physical address of beginning of a segment, but contain a selector that points to a system-level structure called a segment descriptor. A segment descriptor contains the physical address of the beginning of the segment, the length of the segment, and access permissions to that segment. The offset is checked against the length of the segment, with offsets referring to locations outside the segment causing an exception. Offsets referring to locations inside the segment are combined with the physical address of the beginning of the segment to get the physical address corresponding to that offset. The segmented nature can make programming and compiler design difficult because the use of near and far pointers affects performance. Addressing modes. Addressing modes for 16-bit processor modes can be summarized by the formulas @21. 22. Addressing modes for 32-bit x86 processor modes. 23. Can be summarized by the formulas @24. Addressing modes for the 64-bit processor mode can be summarized by the formulas @24.
Okay, did not read all these numbers. I think that's kind of a photo. That's not a text, that's a kind of photo. So it's not reading this text.
Instruction relative addressing in 64-bit code, RIP and displacement, where RIP is the instruction pointer register, simplifies the implementation of position-independent code, as used in shared libraries in some operating systems. 25. The 8086 had 64 kilobytes of 8-bit, or alternatively 32K word of 16-bit, I/O space, and a 64 kilobytes, 1 segment, stack in memory supported by computer hardware. Only words, 2 bytes, can be pushed to the stack. The stack grows toward numerically lower addresses, with SSSP pointing to the most recent live pushed item. There are 256 interrupts, which can be invoked by both hardware and software. The interrupts can cascade, using the stack to store the return address. X86 registers. 16-bit. The original Intel 8086 and 8088 have 14 16-bit registers. 4 of them, AX, BX, CX, DX, are general-purpose registers, GPRs, although each may have an additional purpose. For example, only seek song be used as a counter with the loop instruction. Each can be accessed as 2 separate bytes. Thus BX shy byte can be accessed as BH and low byte as BL. 2 pointer registers have special roles. SP, stack pointer, points to the top of the stack, and BP, base pointer, is often used to point at some other place in the stack, typically above the local variables. See frame pointer. The registers SI, DI, BX and BP area address registers, and may also be used for array indexing. 4 segment registers, CS, DS, SS and S, are used to form a memory address. The flags register contains flags such as carry flag, overflow flag and zero flag. Finally, the instruction pointer, IP, points to the next instruction that will be fetched from memory and then executed. This register cannot be directly accessed, read or written, by a program. 26. The Intel 80186 and 80188 are essentially an upgraded 8086 or 8088 CPU, respectively, with on-chip peripherals added, and they have the same CPU registers as the 8086 and 8088, in addition to interface registers for the peripherals. The 8086, 8088, 80186, and 80188 can use an optional floating point coprocessor, the 8087. The 8087 appears to the programmer as part of the CPU and adds 8 80-bit wide registers, ST0 to ST7, each of which can hold numeric data in one of 7 formats: 32, 64, or 80-bit floating point, 16, 32, or 64-bit. binary, integer, and 80-bit packed decimal integer. 7, S6, S13, S15. It also has its own 16-bit status register accessible through the FNTSW instruction, and it is common to simply use some of its bits for branching by copying it into the normal flags. 27, in the Intel 80286. To support protected mode, 3 special registers hold descriptor table addresses, GDTR, LDTR, IDTR, and a 4th task register, TR, is used for task switching. The 80287 is the floating point coprocessor for the 80286 and has the same registers as the 8087 with the same data formats. 32-bit. Registers available in the X86-64 instruction set. With the advent of the 32-bit 80386 processor, the 16-bit general-purpose registers, base registers, index registers, instruction pointer, and FLAGs register, but not the segment registers, were expanded to 32 bits. The nomenclature represented his by prefixing an E for extended to their register names in X86 assembly language. Thus, the AX register corresponds to the lowest 16 bits of the new 32-bit EAX register, Psi corresponds to the lowest 16 bits of ESI, and so on. The general-purpose registers, base registers, and index registers can all be used as the base in addressing modes, and all of those registers except for the stack pointer can be used as the index in addressing modes. 2 new segment registers, FS and GS, were added. With a greater number of registers, instructions and operands, the machine code format was expanded. To provide backward compatibility, segments with executable code can be marked as containing either 16-bit or 32-bit instructions. Special prefixes allow inclusion of 32-bit instructions in a 16-bit segment or vice versa. The 80386 had an optional floating point coprocessor. The 80387, it had 8 80-bit wide registers, ST, 0, TOST, 7, 28, like the 8087 and 80287. The 80386 could also use an 80287 coprocessor. 29, with the 80486 and all subsequent X86 models. The floating point processing unit, FPU, is integrated on chip. The Pentium MMX added 8 64-bit MMX integer registers, MMX0 to MMX7, which share lower bits with the 80-bit wide FPU stack. 30, with the Pentium 3, Intel added a 32-bit streaming SIMD extensions, SSE, control /status register, MXCSR, and 8 128-bit SSE floating point registers, XMM0 to XMM7. 31, 64-bit. Starting with the AMD Opteron processor, the X86 architecture extended the 32-bit registers into 64-byte registers in a way similar to how the 16 to 32-bit extension took place. An R prefix, for register, identifies the 64-bit registers, RAX, RBX, RCX, RDX, RSI, RDI, RBP, RSP, flags, RIP, and 8 additional 64-bit general registers, R8 R15, were also introduced in the creation of X86-64. However, these extensions are only usable in 64-bit mode, which is one of the 2 modes only available in long mode. The addressing modes were not dramatically changed from 32-bit mode, except that addressing was extended to 64 bits. Virtual addresses are now sign extended to 64 bits, in order to disallow mode bits in virtual.
Yes, let's drink some cola. That was 1 hour. So now it's 6 p.m. soon. Let's put this water in the sink. Of course, I not understand much. I understand